In this video, we will learn about the architecture of the Kubernetes system. This diagram from the Kubernetes documentation highlights the main components in a Kubernetes system. A deployment of Kubernetes is called a cluster. On the left side of this diagram is the control plane, which makes decisions about the cluster and detects and responds to events in the cluster. An example of a decision made by the control plane is scheduling of workloads. An example of responding to an event is creating new resources when an application is deployed. The control plane consists of several components. First is the Kubernetes API server, which exposes the Kubernetes API. All communications in the cluster utilizes this API. For example, the Kubernetes API server accepts commands to view or change the state of the cluster. Next is etcd, a highly available key-value store that contains all the cluster data. When you tell Kubernetes to deploy your application, that deployment configuration is stored in etcd. etcd is thus the source of truth for the state in a Kubernetes cluster, and the system works to bring the cluster state into line with what is stored in etcd. The Kubernetes scheduler assigns newly created pods to nodes. This means that the scheduler determines where your workload should run within the cluster. We'll learn more about pods and nodes soon. The Kubernetes Controller Manager runs all the controller processes that monitor the cluster state and ensure that the actual state of a cluster matches the desired state. We'll discuss controllers shortly as well. Finally, the Cloud Controller Manager runs controllers that interact with the underlying cloud providers. These controllers effectively link clusters into a cloud provider's API. Since Kubernetes is open source software and would ideally be adopted by a variety of cloud providers and organizations, it strives to be as cloud agnostic as possible. The Cloud Controller Manager enables both Kubernetes and the cloud providers to evolve freely without introducing dependencies on the other. That covers the control plane on the left side of the diagram. Let's now zoom in on the right side to learn more about the worker nodes. Nodes are the worker machines in a Kubernetes cluster. In other words, user applications are run on nodes. Nodes can be virtual or physical machines. Each node is managed by the control plane and is able to run pods, which again we will learn about in the next video. Nodes are not created by Kubernetes itself, but rather by the cloud provider. This enables Kubernetes to run on a variety of infrastructures. The nodes are then managed by the control plane. The components on a node enable that node to run pods. First is the kubelet, the most important component. This controller communicates with the Kubernetes API server to receive new and modified pod specifications and ensure that those pods and their associated containers are running as desired. The kubelet also reports to the control plane on health and status. In order to start a pod, the kubelet uses the container runtime, which we touched on in our first module. The container runtime is responsible for downloading images and running containers. Rather than providing a single container runtime, Kubernetes implements a container runtime interface that permits pluggability of the container runtime. While Docker is likely the best known runtime, Rocket and CRIO are two other commonly used container runtimes. Lastly, the Kubernetes proxy is a network proxy that runs on each node in a cluster. This proxy maintains network rules that allow communication to pods running on nodes. In other words, communication to workloads running on your cluster. This communication can come from within or outside of the cluster. We've mentioned controllers a few times. Controllers ensure that the actual state of the cluster matches the desired state. But to understand this better, the Kubernetes documentation gives a great definition of and analogy for controllers. A control loop is defined as a non-terminating loop that regulates the state of a system. A great example of a control loop is a thermostat. When you set the temperature on a thermostat, you specify the desired state. You would like the room to be, say, 70 degrees Fahrenheit. The thermostat then works continually to make the actual state, the temperature in the room, closer to the desired state, the temperature set on the thermostat. Controllers in Kubernetes work the same way, but they watch the state of a Kubernetes cluster and take action to ensure that the cluster's state matches the desired state. Generally, the controller will send a message to the API server to initiate an action that will help bring the current state in line with the desired state. A Kubernetes controller tracks a Kubernetes object. If, for example, you specify that you'd like 3 instances of your application to run in Kubernetes, controllers will monitor the state of your cluster and ensure, to the best of their ability and within the constraints of the system, that 3 instances of your application are in fact running at any given time. We'll learn more about Kubernetes objects and controllers in the next video. You should now be familiar with the architecture of a Kubernetes cluster. Specifically, you should understand that there is a control plane made up of several components which makes global decisions about the cluster. You should also understand that there are separate nodes that run important Kubernetes components as well as user workloads deployed on the cluster. Finally, you should know what a controller is and how Kubernetes uses it to realize the appropriate state in a cluster. In the next video, we'll learn about Kubernetes objects, which are resources that can be created in a cluster.